Welcome students to the new course of Signals and Systems. In this course, we will study in detail about signals, its importance. We'll discuss various fundamental signals, then we will move towards system part. Before going in detail about the basics of signals, I will recommend some books for the same. You have some important books which you can go through some important books regarding the same. I will write down here. These are the fundamental books which you can consult. First one is Open Hand, Signals and Systems by Open Hand. Signals and Systems. This is by Open Hand. Very important book. You can read this book. It's a pretty good book. Then you have Simon Hacken, Signals and Systems by Simon Hykins. Or you can consult for numerical problems so that you will get acquainted with the numerical problems and you will not face any difficulties in competitive exams or in gate exam sham series. These are the three recommended books. You can go for these two books. These are very good books. Now, before going for the signal definition of signal, what's the need? Why we study signals? Why we study signals? This subject is pretty important subject. It will help you in the subsequent courses like in DSP. It will also help you in any type of processing whenever you go for signal processing research. This is the basic fundamental subject for all these subjects. So you must have a pretty good base in signals and systems, especially in signal bar. So what's the reason why we go for signals study? Why we study signals? A reason simple, in order to find the expression for the response of a system. That means you can say in order to find the expression of the response, in order to find the expression for the response of the system given electrical input and system as mathematical model and system as mathematical models. So you study signals so that you can find the expression for the response of a system. That means you have some system, you give input to a system, means you give some kind of excitation to a system, then you will get, after processing of that very input, you will get the response, and you are trying to find the expression for the response of a system given you give electrical input, and system can model as a system can be written as a mathematical model. Model just a system so that you can find the expression of the response of the system. That means the response means output expression overall you can find. So this is the reason why we study signals. So we will just write down the definition of a signal. So what do you mean by signal? Basic definition of a signal: any entity having associated information with it is called as a signal. I will write down here. So any entity having associated information with it is called as a signal. Here you have voltages and currents are always signal inputs, are always signal inputs. You just remember they're always signal inputs and not bias inputs. Bias means you're just giving some voltage. So these are just signal inputs, not biasing input. So signal definition is any entity having associated information with it is termed as a signal. Now, signal can be a function, one dimension signal, that means it's a function of a single variable, or it may be a function of two variables, two independent variables. Then signal will be called as 2D signal. Maybe signal will be a function of three variables. Then it is a three-dimension signal. We will just study some detail about the same. So signal, we will say in general, we have f of t, this is a signal, and this is a function of time, and time here, this time t. This is independent variable. You must remember that this is independent variable. This type of signal, which is a function of one variable, that's time, it's always 1D signal. Similarly, signal need not always function of time. Signals need not always be a function of time. Signals need not always be functions of time. Functions of time. That means you have some signal, they are not dependent on time. Suppose example for the same is picture. You have a picture signal. Picture signal is a function of coordinate x and y. It's a function of x and y coordinate system, because picture is in terms of pixel. Then you have a grayscale, there will be some x value and y value. That means it's a function of x and y. This is not a function of time, so you can just show f of x y. This is a picture, and this is function of two variables, and this is 2D signal. Similarly, we have 3D signal. In 3D signal, signal will be a function of three independent variables like this, f, x, y, t. Because if you have number of pictures, then you have a function of f of x, y. If the picture is moving, that means video, that means time. With respect to time, you have pictures that changing, and you will get the video. So video is a function of x, y, as well as time. Got it? So this is a 3D signal example. Now I will discuss a little bit about a representation of signals. A representation of signals. So you have a representation of signals. Signals can be either defined graphically or mathematically. Signals can be either defined graphically or mathematically. Suppose we have rectangular, I will just, that means signal can be represented either mathematically or graphically. Now we will take some examples and represent them mathematically as well as graphically. First signal example which you can represent is rectangular pulse. Rectangular pulse. You have a rectangular pulse signal. Now you just represent the same signal in two different representation. One will be graphical representation and another will be mathematical representation. So I will just try to represent the signal in terms of graphical first of all. So you have this in two dimension. You will represent this as a function in independent variable time, and this will be your f of t, and the value here is 1. That means this is minus t by 2 and this will be t by 2. So this is rectangular pulse signal. That means its value will be always equal to 1 from minus, when t will take the value from minus t by 2 to t by 2, and its function value will be always 0 other than this range. So this is graphical representation. Graphical representation of signal. Which signal? This is rectangular pulse. Then the same signal can be represented in terms of mathematical expression. You just try to show the mathematical expression for the same signal. How can you define this mathematical? Mathematically, you can write down f of t is equal to 1 when t value, that means independent value, it's equal to minus t by 2 to t by 2 and 0 otherwise. Otherwise means all the other values of t otherwise. Means outside this range you will have the value of f of t equal to 0 outside this range. So this representation is mathematical representation of signal. Mathematical representation of signal. Of which signal? Rectangular pulse. Rectangular signal t. So this is the representation of signal. That means any type of signal you can represent either mathematically or graphically. So that's for the today's lecture. That's it for the today's lecture. Inshallah, we will discuss more about signals and systems tomorrow. Basically, we will study in detail. We will represent different signals. Then, accordingly, we will discuss them one by one. Thank you.